Welcome. Find a comfortable position, somewhere you can truly settle, where the weight of the day begins to dissolve like starlight fading into dawn. Tonight, we're embarking on a journey through one of the universe's most profound mysteries, black holes, and exploring the deep psychological currents that flow when we contemplate the vastness of space. This isn't just a story about cosmic phenomena, it's an invitation to release, to surrender into the infinite, to find peace in the very vastness that sometimes unsettles us. As you listen, allow your breath to slow, to deepen. There's nowhere you need to be, nothing you need to do, just listen. Simply listen. Let the words wash over you like gentle waves, carrying away tension, carrying away the accumulated weight of 1,000 small concerns. We'll move slowly through the cosmos together, pausing often, allowing silence to speak as eloquently as words. Black holes. Even the name carries a certain gravity, doesn't it? A weight, a pull. These cosmic entities have captivated human imagination since their theoretical prediction emerged from Einstein's equations over a century ago. They represent boundaries, edges of understanding, thresholds between the known and the unknowable. And perhaps that's why they fascinate us so deeply, why they appear in our dreams and our fears, why they serve as perfect metaphors for the mysteries we carry within ourselves. But before we approach these cosmic thresholds, before we stand at the edge of event horizons and peer into singularities, we must understand where black holes come from. We must witness their birth. And that birth begins not in darkness, but in light, in the brilliant, burning life of stars. Imagine, if you will, a star. Not just any star, but a massive one, perhaps 20 times, 30 times, even 50 times the mass of our own sun. Picture it suspended in the velvet darkness of space, a sphere of incandescent plasma, burning with a fury that has persisted for millions of years. This star is a furnace, a cosmic forge where the simplest elements are transformed into more complex ones through the alchemy of nuclear fusion. Deep in its core, hydrogen atoms collide with such tremendous force that they fuse together, forming helium and releasing vast quantities of energy in the process. This energy, this outward pressure of radiation and heat, is what keeps the star from collapsing under its own immense gravitational weight. It's a delicate balance, a cosmic dance between the inward pull of gravity and the outward push of fusion. For millions of years, this equilibrium holds. The star shines steadily, a beacon in the darkness. Take a moment here, breathe with the rhythm of that stellar furnace. Inhale, the gathering of hydrogen, the compression, the building pressure. Exhale, the release of energy, the outward flow of light, the steady burning. Feel how your own body maintains its balances. Temperature, breath, heartbeat, just as the star maintains its equilibrium between collapse and explosion, but nothing lasts forever. Eventually, after millions or even billions of years, the hydrogen fuel in the star's core begins to run out. The fusion reactions that have sustained the star for so long start to wane, and when they do, the delicate balance shifts. Gravity, patient and inexorable, begins to win. As the core's hydrogen depletes, the star responds by contracting slightly, which increases the temperature and pressure in its core. This allows helium fusion to begin, helium atoms fusing into carbon and oxygen. The star enters a new phase of life, burning helium now instead of hydrogen. But this phase doesn't last as long. Helium burns faster, more furiously, and when the helium runs out, if the star is massive enough, it contracts again, heating up further, allowing carbon to fuse into heavier elements: neon, magnesium, silicon. Each successive stage of fusion happens more quickly than the last. A star might burn hydrogen for 10 million years, helium for 1 million years, carbon for 1,000 years, silicon for just a few days. It's like watching a cosmic clock wind down, each tick faster than the one before, each moment more urgent, more intense. In these final stages, the star develops a layered structure, like an onion. The outermost layers still contain hydrogen. Beneath that, a shell of helium, then carbon and oxygen, neon and magnesium, silicon and sulfur. And at the very center, in the core, iron begins to accumulate. Iron. In the cosmic economy of nuclear fusion, iron is bankruptcy. Fusing iron doesn't release energy, it consumes energy. When a massive star's core becomes predominantly iron, the game is over. There's no more fuel to burn, no more fusion reactions to generate the outward pressure needed to resist gravity's inward pull. Let your awareness settle on this moment of cosmic transition. The star has burned brilliantly for millions of years, transforming lighter elements into heavier ones, radiating light and warmth into the surrounding space. But now, with an iron core at its center, it stands at a threshold. The balance that has sustained it for so long is about to break. Gravity is about to claim its victory. And it happens fast, catastrophically fast. The iron core, no longer supported by fusion energy, begins to collapse. Not slowly, not gradually, but in a fraction of a second. Electrons are forced into protons, creating neutrons and releasing neutrinos in a process called neutronization. The core, which might have been roughly the size of Earth, collapses to a sphere perhaps 20 kilometers across, a neutron star, in less than a second. The collapse happens so rapidly that the outer layers of the star don't immediately realize what's occurring at the center. They're still falling inward, still being pulled by gravity, when suddenly they encounter the incredibly dense neutron core. It's like a cosmic traffic accident, matter falling inward at a significant fraction of the speed of light suddenly meets an immovable barrier. The result is a rebound, a shock wave that propagates outward through the star's layers with unimaginable violence. This is a supernova, one of the most energetic events in the universe. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion hurls the star's outer layers into space at speeds of tens of thousands of kilometers per second, enriching the interstellar medium with all those heavy elements forged in the star's core: the carbon, oxygen, iron, and gold that will eventually become part of new stars, new planets, new life. But we're not here for the explosion, magnificent as it is. We're here for what remains behind. If the original star was massive enough, roughly 25 to 30 times the mass of the Sun or more, even the neutron core cannot withstand gravity's pull. The collapse continues. Neutrons themselves are compressed beyond their ability to resist. There is no known force in physics that can stop the collapse now. The core continues to contract, becoming smaller and denser until it crosses a threshold from which there is no return. It becomes a black hole. Breathe here. Let that transformation settle into your awareness. A star that once blazed with the light of millions of suns has collapsed into a region of space so dense, so gravitationally intense, that not even light can escape. From maximum luminosity to perfect darkness, from vast stellar sphere to infinitesimal point. It's a transformation as complete as any in nature, like the caterpillar that dissolves entirely within the chrysalis before reforming as a butterfly, except here, The butterfly is darkness itself. This is how stellar mass black holes are born, from the deaths of massive stars, from the surrender of matter to gravity's ultimate embrace. But there are other types of black holes, formed through different processes, existing at different scales. Stellar mass black holes, born from collapsing stars, typically range from about 5 to several dozen times the mass of our Sun. They're scattered throughout galaxies, invisible markers of stellar death, detectable only through their gravitational effects on nearby matter or companion stars. Then there are intermediate mass black holes, ranging from hundreds to thousands of solar masses. These are more mysterious, less well understood. They might form from the merger of smaller black holes, or from the direct collapse of very massive stars in the early universe, or through other processes we're still working to understand. Recent research from 2024 has identified several promising candidates for intermediate mass black holes in dense star clusters, suggesting they might be more common than previously thought. And then, at the other end of the scale, there are the supermassive black holes. These cosmic giants lurk at the centers of most large galaxies, including our own Milky Way. They contain millions or even billions of times the mass of the Sun. The supermassive black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. The black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope in 2019 and refined in subsequent observations through 2024, contains about 6.5 billion solar masses. How do supermassive black holes form? This remains one of the great questions in astrophysics. They might grow from stellar mass black holes that consume vast amounts of matter over billions of years. They might form from the direct collapse of enormous gas clouds in the early universe. They might grow through mergers, smaller black holes combining into larger ones. Recent gravitational wave observations from LIGO and Virgo detectors have confirmed that black hole mergers do occur, and sophisticated computer simulations in 2024 have shown how these mergers might build up supermassive black holes over cosmic time. Let your mind expand to hold these scales. From black holes just a few times the mass of our Sun, to monsters billions of times more massive. From objects a few dozen kilometers across to regions that would encompass our entire solar system. The universe operates at scales that dwarf human comprehension, and black holes exemplify this cosmic grandeur. But regardless of their size or origin, all black holes share certain fundamental properties. They all warp spacetime around them. They all possess an event horizon, that boundary beyond which nothing can escape. And they all, at their centers, contain a singularity, a point where our current understanding of physics breaks down. Let's approach these features slowly, carefully, with the reverence they deserve. To understand black holes, we must first understand gravity, not as Newton conceived it, as a force acting at a distance, but as Einstein revealed it, as the curvature of spacetime itself. Imagine spacetime as a fabric, a flexible sheet stretched taut. In the absence of matter or energy, this fabric is flat, smooth, undistorted. But place a mass on this fabric, a star, a planet, even a person, and it creates a depression, a curvature. The more massive the object, the deeper the depression. This curvature is what we experience as gravity. When Earth orbits the Sun, It's not being pulled by an invisible force. It's following the curved path through space-time created by the sun's mass. It's like a marble rolling around the depression created by a bowling ball on a stretched rubber sheet. The marble isn't being pulled by the bowling ball, it's simply following the curved surface. This is Einstein's great insight from his general theory of relativity, published in 1915 and confirmed through countless observations and experiments over the past century. Gravity isn't a force, it's geometry. Mass tells space-time how to curve, and curved space-time tells mass how to move. Now imagine increasing the mass of an object while keeping its size the same, or compressing the same mass into a smaller and smaller volume. The curvature of space-time becomes more pronounced, steeper, more extreme. A planet creates a gentle depression. A white dwarf star creates a deeper one. A neutron star creates a steep-sided pit. And a black hole? A black hole creates a curvature so extreme that space-time essentially folds in on itself, creating a one-way passage into a region from which nothing, not matter, not light, not information, can escape. Take a moment to visualize this. See the fabric of space-time, smooth and flat. Now watch as a massive star collapses, compressing its mass into a smaller and smaller region. Watch the depression in space-time deepen, the sides becoming steeper and steeper until finally they become vertical, infinite. The fabric doesn't just curve, it tears, creating a hole, a void, a place where the normal rules of space and time cease to apply in the ways we understand them. This is the event horizon, the boundary of no return. The event horizon is not a physical surface. You couldn't touch it, couldn't bounce a ball off it. It's a mathematical boundary, a point of no return defined by the escape velocity reaching the speed of light. Inside the event horizon, you would need to travel faster than light to escape. And since nothing can travel faster than light, nothing can escape. For a non-rotating black hole, what physicists call a Schwarzschild-Schwarzschild black hole, after Carl Schwarzschild-Schwarzschild, who found the first exact solution to Einstein's equations just months after general relativity was published. The event horizon is a perfect sphere. Its radius, called the Schwarzschild-Schwarzschild radius, depends only on the black hole's mass. For a black hole with the mass of our Sun, the Schwarzschild-Schwarzschild radius would be about 3 kilometers. For the supermassive black hole at the center of our galaxy, it's about 12 million kilometers, roughly 17 times the radius of the Sun. But most black holes aren't perfectly spherical. They rotate, sometimes very rapidly, because they form from rotating stars, and conservation of angular momentum means that as the star collapses, its rotation speeds up, like a figure skater pulling in their arms during a spin. A rotating black hole, called a Kerr black hole after Roy Kerr, who solved the equations for rotating black holes in 1963, has a more complex structure. It has an event horizon, but also an outer boundary called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Imagine standing near a rotating black hole, outside the event horizon, but within the ergosphere. Space-time itself is being pulled around the black hole, and you're being pulled with it, like a leaf caught in a whirlpool. You could still escape. You're outside the event horizon, but you couldn't stand still. You'd be forced to move in the direction of the black hole's rotation, dragged along by the rotating space-time itself. This frame-dragging effect, predicted by general relativity and confirmed by observations of rotating neutron stars and black holes, is one of the most mind-bending consequences of Einstein's theory. It's not just that massive objects curve space. Rotating massive objects drag space-time around with them, like honey being stirred in a jar. Now, imagine crossing the event horizon. What would you experience? From your perspective, falling toward a black hole, something strange would happen. As you approach the event horizon, you'd notice that the black hole appears to grow larger, filling more and more of your field of view. The stars behind you would appear to shift and distort, their light bent by the black hole's gravity. If you looked carefully, you might even see multiple images of the same star, their light taking different curved paths through space-time to reach your eyes. Time would also behave strangely. According to general relativity, time passes more slowly in stronger gravitational fields, an effect called gravitational time dilation. As you fell closer to the event horizon, time for you would pass normally, but if you could somehow look back at the universe you left behind, you'd see it speeding up. Stars would age rapidly, galaxies would evolve, the universe would rush forward through time. And then you'd cross the event horizon. From your perspective, nothing special would happen at that exact moment. There'd be no barrier, no sensation of crossing a boundary. You'd simply continue falling, but you'd have crossed a point of no return. Every direction you could travel would lead further into the black hole. Even if you pointed yourself directly away from the center and accelerated at the maximum possible rate, you'd still be pulled inexorably inward. The future direction of time itself now points toward the singularity at the center. Let this sink in. Breathe with it. Inside the event horizon, the singularity isn't just in your future. It is your future. It's as inevitable as tomorrow, as unavoidable as the next moment. This is what it means for space-time to be curved so extremely that all paths lead inward. But what would an outside observer see? This is where things become even stranger. If someone watched you fall toward a black hole from a safe distance, they would never see you cross the event horizon. Never. As you approached the event horizon, they would see you moving more and more slowly, your image becoming more and more red-shifted as the light from your body struggled to escape the black hole's gravitational pull. You would appear to freeze, asymptotically approaching the event horizon, but never quite reaching it, your image fading and reddening until it became invisible. This is why black holes were once called frozen stars, because from the outside, matter appears to freeze at the event horizon, never quite falling in. But this is an illusion created by the extreme time dilation. From your perspective, you'd cross the event horizon in a finite amount of time. From the outside perspective, it would take infinite time. Both perspectives are valid. They're simply different ways of slicing up the curved space-time around the black hole. This leads to a profound puzzle that physicists are still grappling with: the black hole information paradox. If matter falls into a black hole and, from the outside perspective, never quite crosses the event horizon, what happens to the information encoded in that matter? Does it remain somehow encoded on the event horizon? Does it get destroyed when it reaches the singularity? Or does it escape somehow, perhaps through Hawking radiation? Stephen Hawking's groundbreaking work in the 1970s showed that black holes aren't entirely black, Through quantum mechanical effects near the event horizon, black holes emit radiation, now called Hawking radiation, and slowly evaporate over time. For stellar mass black holes, this evaporation takes far longer than the current age of the universe, but for tiny black holes, it could happen quickly. Recent theoretical work in 2024 has refined our understanding of Hawking radiation and suggested possible ways that information might be preserved, perhaps encoded in subtle correlations in the radiation itself. But we're getting ahead of ourselves. Before we explore Hawking radiation and black hole evaporation, we need to understand what happens as you continue falling past the event horizon into the increasingly extreme gravitational field closer to the center. We need to talk about spaghettification. Gravity doesn't pull uniformly. If you're standing on Earth, your feet are slightly closer to Earth's center than your head, so they experience slightly stronger gravity. The difference is tiny, far too small to notice, but it's there. This difference in gravitational force across an object is called a tidal force, and it's what causes ocean tides on Earth. The moon's gravity pulls slightly more strongly on the side of Earth facing the moon than on the far side, creating a bulge of water, a tide. Near a black hole, tidal forces become extreme. Imagine falling feet first toward a stellar mass black hole. Your feet are closer to the black hole than your head, so they experience stronger gravity. They're pulled harder. The difference in gravitational force between your feet and your head becomes enormous, strong enough to stretch you, to pull you apart. This is spaghettification, sometimes called the noodle effect. As you fall toward a black hole, you'd be stretched lengthwise and compressed sideways, elongated like a piece of spaghetti. For a stellar mass black hole, this would happen well before you reached the event horizon. The tidal forces would tear you apart at the molecular level, then the atomic level, reducing you to a stream of particles spiraling into the black hole. It sounds horrific, but remember, we're exploring these cosmic phenomena not to frighten, but to understand, to find a strange peace in the universe's most extreme processes. Spaghettification is simply gravity doing what gravity does, creating order from chaos in its own inexorable way. Theoretical work refined our understanding of how black holes form and behave. But it wasn't until the 21st century that we obtained direct evidence. The detection of gravitational waves in 2015 provided the first direct observation of black holes, not through light they emitted or affected, but through the ripples they created in space-time itself. The Event Horizon Telescope image in 2019 showed the shadow of a black hole for the first time, confirming predictions made decades earlier. And the pace of discovery continues to accelerate. In 2024 alone, we've detected hundreds of gravitational wave events, imaged multiple black holes with increasing resolution, discovered new populations of intermediate mass black holes, and refined our theoretical understanding of quantum effects near event horizons. This progress is a testament to human curiosity, ingenuity, and persistence. Black holes, once purely theoretical, once thought to be unobservable, are now objects we can study in detail, can image, can use to test our most fundamental theories of physics. And we're not done. Future gravitational wave detectors, like the space-based LISA mission planned for the 2030s, will detect supermassive black hole mergers across the entire universe. Next-generation telescopes will image black holes in unprecedented detail. Advances in quantum gravity theory may finally resolve the singularity, may tell us what really happens at the center of a black hole. The universe is revealing its secrets, slowly, patiently, to those who ask the right questions and look carefully. And this process of discovery, this gradual illumination of cosmic mysteries, is itself a source of meaning and wonder. We live in an age of cosmic discovery. We're learning things about the universe that no previous generation could have known. We're seeing things, black holes, gravitational waves, the cosmic web of galaxies that were invisible to our ancestors. We're part of a grand human project of understanding, of pushing back the boundaries of ignorance, of bringing light to darkness. And you, by engaging with these ideas, by contemplating these cosmic phenomena, are part of that project. You're participating in the human endeavor to understand the universe. You're exercising the capacity for wonder and curiosity that makes us human. One of the deepest mysteries in physics is the arrow of time, why time seems to flow in one direction, from past to future, why we remember the past but not the future, why entropy disorder increases over time. Black holes are intimately connected to this mystery. In the 1970s, physicist Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or information content. Specifically, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was surprising and profound, suggesting deep connections between gravity, quantum mechanics, and thermodynamics. The second law of thermodynamics states that the total entropy of a closed system always increases over time. This is the arrow of time, the reason why eggs break but don't spontaneously reassemble, why heat flows from hot to cold but not the reverse, why we age and remember the past but not the future. Black holes fit into this picture in a remarkable way. When matter falls into a black hole, it might seem like entropy is decreasing. The matter becomes more ordered, compressed into a smaller region. But Bekenstein and Hawking showed that the increase in the black hole's entropy, the increase in the area of its event horizon, more than compensates for any decrease in the entropy of the matter. The total entropy still increases, and the second law is preserved. In fact, black holes are the most efficient entropy generators in the universe. A supermassive black hole has more entropy than all the stars in its galaxy combined. The ultimate fate of the universe, in some scenarios, is a state of maximum entropy, where all matter has either evaporated or fallen into black holes, and even the black holes have evaporated through Hawking radiation, leaving only a thin soup of radiation in an ever-expanding space. This might sound bleak, a heat death, a final state of maximum disorder and minimum structure. But it's also a kind of completion, a return to simplicity, a cosmic exhale after the long, complex inhale of structure formation. And even this might not be the end. Some theories suggest that quantum fluctuations in the far future could spontaneously create new universes, new big bangs, new cycles of complexity and simplicity. The universe might be eternal, not in the sense of lasting forever in one state, but in the sense of continually transforming, dying, and being reborn in an endless cosmic cycle. These are speculations, of course. We don't know the ultimate fate of the universe. But contemplating these possibilities, deep time, cosmic cycles, the arrow of entropy, can provide a profound sense of perspective. Your life, your concerns, your joys and sorrows, all of these are part of the universe's journey from low entropy to high entropy, from simplicity to complexity, and back to simplicity. You're a temporary eddy in the flow of entropy, a brief local decrease in disorder, your organized body and mind that contributes to the overall increase in cosmic entropy. And there's something beautiful about that. You're not separate from the cosmic flow. You're part of it. Your existence, your consciousness, your capacity to wonder and love and create, all of this is the universe's way of exploring itself, of creating temporary pockets of order and meaning in the long journey toward maximum entropy. Breathe with this understanding. You're a wave in the cosmic ocean, a temporary pattern in the flow. And when the wave subsides, the ocean remains, ready to form new waves, new patterns, new expressions of its infinite creativity. We've touched on this theme several times, but let's explore it more deeply. The paradoxical comfort of cosmic insignificance. In our daily lives, we often feel pressure to be significant, to matter, to make a difference. We worry about our legacy, our impact, whether we'll be remembered. We compare ourselves to others, measure our achievements, strive for recognition and success. This pressure can be exhausting. It can lead to anxiety, burnout, a sense of never being enough. We're constantly trying to prove our significance in a world that seems to demand it. But what if we let go of that pressure? What if we accepted our cosmic insignificance, not as a source of despair, but as a source of freedom? From the cosmic perspective, nothing we do matters in any ultimate sense. The universe doesn't care whether you succeed or fail, whether you're remembered or forgotten. In 1 billion years, the sun will have expanded and engulfed Earth. In 1 trillion years, the stars will have burned out. In 100 billion years, even black holes will have evaporated. Nothing we build will last. Nothing we achieve will be remembered. This could be depressing, but it can also be liberating. If nothing matters cosmically, then we're free to decide what matters to us, personally, locally, temporarily. We're free to create our own meaning, to choose our own values, to live according to our own lights, rather than some cosmic standard. The existentialist philosopher Albert Camus wrote about the absurdity of existence, the gap between our human need for meaning and the universe's indifference. He argued that we should embrace this absurdity, should rebel against it by creating meaning anyway, by living fully and authentically, even in the face of cosmic meaninglessness. Modern psychology has found that this perspective can be healthy. A 2024 study in the Journal of Positive Psychology examined what the researchers called cosmic acceptance, the ability to accept one's insignificance in the cosmic scheme while still finding personal meaning and purpose. They found that people high in cosmic acceptance reported lower anxiety, greater life satisfaction, and more authentic living. They were less concerned with external validation and more focused on intrinsic values and relationships. The key, the researchers found, was balance. People who focused only on cosmic insignificance without finding personal meaning tended toward nihilism and depression. People who denied cosmic insignificance and insisted on cosmic importance tended toward grandiosity and anxiety. But people who could hold both perspectives, I'm cosmically insignificant, and my life has personal meaning showed the best psychological outcomes. This is the wisdom of cosmic perspective, to zoom out, to see yourself as a tiny, temporary part of a vast, ancient universe, and then to zoom back in, to embrace your brief existence, to find meaning and joy and connection in the here and now. You don't matter to the universe, but you matter to yourself, to the people you love, to the small corner of space-time you inhabit. And that's enough. That's more than enough. Let's explore some specific practices you can use to cultivate the sense of cosmic peace we've been discussing. These are practices you can return to whenever you need perspective, whenever you need to release anxiety, whenever you need to reconnect with the vastness. This is the practice we touched on earlier. Lie down or sit comfortably. Close your eyes. Imagine yourself from above, then zoom out progressively. Room, building, city, region, country, continent, Earth, solar system, galaxy, universe. Then zoom back in, returning to your body, your breath. Do this slowly, taking time at each level to really visualize and feel the scale. This practice helps train your mind to shift perspectives, to access the cosmic view when you need it. Go outside on a clear night, or simply imagine a starry sky. Choose a star. Remember that the light entering your eyes left that star years, or decades, or centuries ago. It traveled through the vacuum of space, through the atmosphere, to reach you. You and that star are connected by this light, by the photons that bridge the distance between you. Feel that connection. Extend it to all the stars you can see, to all the galaxies beyond. You're not isolated. You're connected to the cosmos by light, by gravity, by the atoms in your body that came from stars. Sit comfortably and breathe slowly. With each inhale, imagine breathing in deep time, the billions of years of cosmic history, the slow formation of galaxies and stars, the patient work of evolution. With each exhale, release your urgency, your impatience, your sense of time pressure. Let your breath slow to match the cosmic rhythm, slow, patient, unhurried. The universe has all the time in the world. So do you in this moment. This is a more advanced practice, useful for releasing difficult emotions or thoughts. Visualize a black hole, not as something frightening, but as a cosmic recycling center, a place where matter and energy are transformed. Now, imagine placing a difficult emotion, anxiety, anger, grief, near the event horizon. Watch it spiral inward, watch it cross the horizon, watch it disappear into the black hole. It's not destroyed, it's transformed, recycled, returned to the cosmic flow. You can let it go. The universe will take care of it. Place your hand on your chest, feeling your heartbeat. Remember that the atoms in your body were forged in stars, scattered by supernovae, gathered into the solar system, incorporated into Earth, cycled through countless organisms, and now temporarily organized into you. Feel gratitude for this improbable journey, for the cosmic processes that made your existence possible. You're not separate from the universe. You're a way the universe has organized itself to become aware of itself. How remarkable, how precious. These practices, done regularly, can help rewire your brain's response to cosmic contemplation, shifting it from anxiety to awe, from fear to peace. They're not escapes from reality, they're ways of seeing reality more clearly, more completely, from a perspective that includes both the immediate and the cosmic. One final theme to explore: the role of mystery in mental health and well-being. Modern culture often emphasizes certainty, control, and complete understanding. We want answers, solutions, explanations. We're uncomfortable with ambiguity, with not knowing, with mystery. But black holes remind us that mystery is fundamental to the universe. We don't fully understand what happens at the singularity. We don't know if information is truly preserved or destroyed. We don't know what dark matter is, or dark energy, or whether our universe is one of many in a vast multiverse. We don't know the ultimate fate of the cosmos. And that's okay. That's more than okay. It's wonderful. Mystery is what drives science, what motivates exploration, what keeps life interesting. If we knew everything, if there were no more questions to ask, existence would be boring, static, complete. Psychologically, learning to be comfortable with mystery, with not knowing, is a key component of mental health. Anxiety often stems from intolerance of uncertainty, a need to know, to control, to predict. But life is inherently uncertain. We can't know the future. We can't control most of what happens to us. We can't fully understand ourselves or others. Practices like mindfulness and acceptance-based therapies teach us to be okay with this uncertainty, to tolerate not knowing, to accept mystery as a fundamental part of existence. Research has consistently shown that people who can tolerate uncertainty have lower anxiety and better mental health. A 2024 study in behavior research and therapy examined the relationship between cosmic mystery acceptance, comfort with the fundamental mysteries of existence, and mental health. The researchers found that people who could embrace cosmic mystery, who could be comfortable not knowing the answers to big questions, showed greater psychological flexibility, lower existential anxiety, and higher well-being. Black holes, in this sense, are perfect teachers. They embody mystery. They're places where our understanding breaks down, where we encounter the limits of knowledge, and they invite us to be okay with that, to appreciate the mystery rather than fear it, to find wonder in the unknown rather than anxiety. This doesn't mean we stop seeking answers. Science continues to probe the mysteries of black holes, and we continue to learn. But it means we can hold our knowledge lightly, can appreciate what we know while remaining open to what we don't know, can find peace in the journey of discovery rather than demanding the destination of complete understanding. We've journeyed far together, from the physics of black holes to the psychology of cosmic contemplation, from stellar collapse to human consciousness, from event horizons to mental health practices. Let's integrate these threads, bringing them together into a coherent whole. Black holes are real physical objects, extreme expressions of gravity and space-time curvature, born from the deaths of massive stars or the accumulation of matter in galactic centers. They're surrounded by brilliant accretion disks, emit Hawking radiation, merge and create gravitational waves, and slowly evaporate over cosmic time. They're objects of scientific study, windows into the most extreme physics in the universe. But they're also metaphors, symbols, teachers. They represent the unknown, the mysterious, the places where our understanding breaks down. They embody transformation, the death of stars giving birth to something new. They demonstrate the interconnectedness of the cosmos, their gravity reaching across space, their mergers sending ripples through the fabric of space-time itself. And contemplating them, Contemplating black holes and the vastness of space can be therapeutic. It can trigger awe, which reduces self-focus and increases well-being. It can provide perspective, helping us see our concerns within a larger context. It can connect us to something vast, addressing our need to be part of something larger than ourselves. It can teach us to be comfortable with mystery, with uncertainty, with not knowing. The key is approach. If we approach cosmic contemplation with fear, with a focus on isolation and meaninglessness, it can increase anxiety. But if we approach it with openness, with curiosity, with a willingness to feel awe and connection, it can bring peace. This is true not just for cosmic contemplation, but for life in general. Our experience is shaped not just by what happens to us, but by how we relate to what happens, by the perspective we bring, by the meaning we make. Black holes teach us that darkness and light are intertwined, that destruction and creation are part of the same cosmic dance, that endings are also beginnings. They teach us that we're small but connected, insignificant but precious, temporary but part of something eternal. And they teach us that the universe is far stranger and more wonderful than we can fully comprehend. And that's a source not of fear, but of endless wonder. As we come to the end of our journey, let yourself settle more deeply into rest. Your body is heavy, relaxed, supported. Your mind is quiet, spacious, at peace. You've traveled to the most extreme environments in the universe, to the event horizons of black holes, to the singularities at their centers, to the brilliant accretion disks that surround them. You've witnessed the deaths of stars and the births of black holes. You've felt the ripples of gravitational waves and contemplated the quantum whisper of Hawking radiation. And you've turned inward, exploring the psychology of cosmic contemplation, the fears and wonders that arise when we face the vastness of space, the practices that can help us find peace in that vastness. Now, let it all go. Let the concepts dissolve. Let the images fade. Return to simple awareness, simple presence, simple breath. You're here, now, in this moment. You're a temporary pattern in the cosmic flow, a brief eddy in the river of entropy, a way the universe has organized itself to become aware of itself. You're made of stardust, connected to everything, part of the vast web of matter and energy and space-time that encompasses all that is. And for this brief moment, this brief flicker of existence, you're here, breathing, aware, alive. That's enough. That's more than enough. That's everything. As you drift towards sleep, know that the universe holds you. The same gravity that creates black holes keeps you gently pressed against the earth. The same quantum fields that fill the vacuum of space fill every cell of your body. The same laws that govern the cosmos govern your heartbeat, your breath, your neural activity. You're not separate from the universe. You're an expression of it, a manifestation of its infinite creativity, a temporary form taken by the eternal dance of energy and matter. Rest in that knowledge. Rest in the cosmic embrace. Let yourself be held by the vastness, supported by the fabric of space-time itself. The black holes spin in their silent darkness, patient and eternal. The stars burn and die and are reborn. The galaxies wheel through space, following the curved paths laid down by gravity. And you rest, you breathe, you release into sleep. All is well. All is as it should be. The universe unfolds according to its own deep laws, and you're part of that unfolding, a necessary thread in the cosmic tapestry. Sleep now. Let go. Surrender to the darkness, not as something to fear, but as a place of rest, of renewal, of peace. Like matter crossing the event horizon, let yourself cross the threshold into sleep, into dreams, into the quiet darkness where consciousness dissolves and reforms. The cosmos continues its ancient dance. The black holes spin, the stars shine, and you rest in the heart of it all, held by gravity, connected by light, made of stardust. Sleep well, cosmic traveler. Sleep deeply. Sleep peacefully. And if you found some measure of peace in this journey, some perspective, some wonder, consider returning. Consider subscribing so we can explore more cosmic mysteries together, can find more ways to connect the vastness of space with the intimacy of human experience, can continue this shared journey of discovery and awe. But for now, simply rest. Simply breathe. Simply be. The universe is vast, but you are here. The cosmos is ancient, but this moment is now. The mysteries are deep, but your breath is simple, steady, present. Rest in that simplicity. Rest in that presence. Rest in the cosmic embrace. All is well. All is well. All is well. Silence. Deep, spacious silence. The silence of space. The silence of the mind at rest. The silence of the heart at peace. Let that silence hold you. Let it fill you. Let it carry you gently into sleep. Good night, traveler. Good night.